Module 6 in Investigation 1 about Introduction to Rational Functions and the Vertical asymptotes. So before we introducing the radical functions, okay, so general form, I want to talk about the number 1. So number 1 says the National Center for Education Statistics NCESED.gov keeps careful records of the number of degrees awarded in the United States. The given table shows the number of the PhDs awarded to men and women in the US over time. So let F, the model the number of the PhDs awarded to the men in terms of the year T, and then the G model the number of the PhD awarded to the woman in terms of the year T. So what is the value of the F of 1940 and 1890? So this is a T. So you're looking for F of T and G of T. But T is a 1940 in F function, and then the 1890 for the G function. So F of 1940, which is 1940 is right here, which is for the F function is going to be the 2,861 men who got the PhD degree. And then G function, we have to check for the 1890, which is 1890 is not right here, but we need to use a G function, which is 2 women who got a PhD. So 2,861 is a man, and then 2 is a woman. And B, let H, the function that input the year T and the output the value of the ratio F of T over G of T. That is the H of T equal to F of T over G of T. What is the value of the H of 1880 and what does it represent this context? So H of 1880 means we put the F of 1880 over G of 1880. So F of 1880 is going to be the number of the PhD awarded to the men at the 1880. And then the G of 1880 means number of the women who got the PhD at the 1880. So the 1880, there are 50 men got a PhD, and then there are 3 women got a PhD. So if I reduce, it's a 17. So there are 17 men per 1 woman. That's a ratio. So ratio of the number of the people who got the PhD as a man over woman. So C, as T varies from the 1890 to the 1900, does the value of the H increases or decreases? So I want to actually check it out. So what I want to do is I want to fill it in. So the last column, since is the blank, I'm going to fill the H of T function here, which is going to be the F of T over G of T. So 1880, which is F of 1880 divided by G of 1880, which is a 15 over 3, a 51 over 3, which is going to be a 17. And then the second one, 147 divided by 2, I got 73.5. And then 1900, 359 over 23, I got 15 over 0.61. And then the 1920, 522 divided by 93, I got 5.61. And the next one is a 2,861 divided by 429. I have a 6.67. Next one is 8,801 divided by 1,028, which is 8.56. And then I got 69,526 divided by 26,105. It's a 2.66. And then the 64,171 and the 55,414 in 2000 is 1.16. And then 76,605 divided by 81,953 is going to be 0.93. So as the T varied from the 1890 to the 1900, so when we have a H of 1890, which is going to be the 1890 was 2.66, and then H of 1900, which is 1561. So what we do is, not the 1900, sorry about that, I put it, okay? So 1890 was 73.5, sorry about that. So look at the number. Is it decreasing or increasing? It's a decreases. Okay, so the value of the H of T is a decreases from the 1890 to the 1900. But still, the both of the number of the PhD in each year is increases though. But what I can say is the rate of the number of the women who get the PhD is faster than the man. Alright, indeed, using the given axis, label the axis based on the input and output quantities for H. Then plot the points of 1880 and then H of 1880 and then 1890 of H and so let's put those 3 points from here. So before that, I want to put the T for the year, and then the y-axis is gonna be the ratio of the man and woman who awarded to earn the PhD degree. So on the x-axis, which is I didn't start from the 0 year, right? So I want to say about this is gonna be I want to say 1880, and then I'm gonna cut it up as every 2 to get the 10 years have passed. Okay, so 1880, which is now the next one is 1890. And then I got the 1900. And then 1920. Is it too short? Okay, let me see. So 1880, okay, so in 1890, let's say put a 1900 here. Sorry about that. So I think that's a better way to. Okay, so I want to put the 1880 and 90 and 1900. And then 910, 920. And then 910, 930, 940. And then 950, 960. 970, 980. And then the 99, 2000. And then it's a 2010. Okay, that fit it. Okay, for the vertical axis, every 2, I want to say 4, 8, 12, and 16. Alright, so 1880 ratio was a 17. So 17. Yeah, put that as a ratio here, right? So 1880, which is 17 is about here, right? Let me put the about here. And then 18 is really up here somewhere, right? And then 19 is 15, 21, so 12, so which is 14, so about 1900, right? So about here. And then 1920 was 5.61, which is 5.61 is about here. And then the 1940, so but I need to put this 3, right? So up to the 1900, so I should put this one here. So very up here. So for this case, for the 1900 is really up here, right? Okay, so that's for D. Then what must be true in this context if the h of t is a 3? So h of 3 means what is the year that the ratio of the number of the men and women who get the PhD. So this time, if h of t equal to 3, then there were 3 times as many PhDs awarded to men in year T than the number of PhDs awarded to women in the United States. Okay, and then if the h of t equal to 1 means now there is the same as a PhD awarded to the man, year T, than the number of the PhD awarded to the woman. Okay, so same amount number because the ratio becomes 1. So F, is it possible for the output of the H be less than 1 in this context? It does, isn't it? Which is at 2010, okay, 2010, the ratio is 0.93. So at the time, there are more women got a PhD than the men. Is it possible for the output of the H to be negative? Well, the smallest number you can get is actually the 0. So in order to get a 0, that means there's no man got a PhD, and then there's some woman got a let's say 10 women got the PhD, right? So this is equal to 0, right? So yeah, number can be the negative number. That's not possible. Okay, so always stays a positive. Okay. All right, next page. Now the H. Must there be a maximum value for h of t in this context? So in order to get a maximum number, the smallest way that I can put it is 1 woman got a PhD, and then let's say 1 million men got a PhD, right? So the ratio is going to be 1 million. But what if there's a 2 million and 1 billion, trillion, So yeah, I don't think there's no maximum. So no maximums on here. Maximums available, okay? Then I use the empty column for the previous page to record the value, which is I did already. Then plot each of the entries of the column as a point on your graph. All right, so let's fill it up. So 1890 was the 5.61. 15.61, isn't it? And the 1920 was a 5.61. So here, 1940 is 6.67, so a little more than that. And then the 1960 is 8.56. And then 1980 is a 2.66. And then the 2000 is 1.66. And then the 0.93. It's getting smaller and smaller, isn't it? So if you connected it, this is going to be something like this, isn't it? So getting smaller and smaller. Something over here. Okay? All right. Then let's do the number 2. Consider the function f of x equals 2 over x. What happened to the value of the function when x gets close to 0? So as you notice, close to 0 means this is actually getting close to 0, right? And also this way is getting close to 0. So let's see what happened for the f of x. So if you plug it in negative 2 as 2 over negative 2 is a negative 1. And 2 over negative 1 is negative 2. And then 2 over negative 0.1 is negative 20, and 2 over negative 0.01 is negative 200. And then 2 over negative 0.001 is negative 2000. So the x value is getting and smaller and smaller, right? Well, the y value is getting smaller and smaller when x gets to the approaching to the 0. And then for the x, I'm going to put it into the other way, okay? So when x equal to 2 into the other function, which is a positive x, and I got 1. Then the plug in 1, 2, plug in that is 20, and 200, and then 2000. So it's getting bigger and bigger too, right? So as the value of x gets close to 0, then the function values, which is f of x, have magnitude, which is the absolute value you put it, that very gets large. Gets the very large, okay? No, I'm saying here. So get very large. So when x is a negative, close to 0, function values are large magnitude, negative number. And x positive is close to 0, the function value are large magnitude, positive numbers. So magnitude is going to be very large, very large. But so the meaning of the graph is when x is getting close from the right, okay, and then it's getting bigger and bigger this ways, and then when x is getting closer from the left, and then getting smaller and smaller, but the magnitude is very large and large, okay. So I can introduce the approaching means. So x approaches the 0, okay. So this is actually that we call that as approaching. All right, the next numbers, I want to do number 5. In number 5, and now f of x is equal to 1 over x minus 8. Complete the following. So complete the following table of the value. To pay attention to the value of the numerator and denominator as you perform your calculations. So now your function is 1 over x minus 8. Plug it in 7. So you got 1 over 7 minus 8, which is negative 1. Now you plug it in 1 over 7.5 minus 8, which is negative 2. And then 1 over 7.9 minus 8 is negative 10. And 1 over 7.99 minus is negative 100. 1 over 7.999 minus 8 is a negative 1000. Now, other side of the 8. So 8.001, which is 1000. 8.01 is 100. 8.1 is a 10, and 2 and 1, okay? So now what we're going to do is we are approaching to the 8 from the both sides, okay? So B, what do you notice as when as x approaches the 8 from the left? So x approaches 8 from the left. Left means that this negative sign is going to be the left, okay? How does it happen? What happened is f of x actually decreases, which is from the negative 1, negative 2, and then become negative 1000, right? Without bound. It goes to infinity. And then see, what do you notice as x approaches 8 from the right? So as x approaches 8 from the right, and then what does this happen? Which means f of x actually increases without bound. Why? Because it was a 1 to 10, 100, and 1000. So you are using the calculator graph f, discuss the group, right? So actually I'll show you what happened when I using the graphing calculator, okay? So I use the decimals to show this. All right, so let's look at the decimals to check that out. So my graph is f of x equaled, and then 1 over x minus 8. So if I'm looking at the 8, okay, so let me see what happened here. So I need to make a really, yeah. So when x is approaching to the 8 from the left, which means you're looking at this graphs, okay? Then what happened is when x approaching the 8 from the left, do you see that the y value getting smaller and smaller, right? That's what we call the without bounds. And then when x approaches to the right from the left, let's see what happened. Do you see the y value getting bigger and bigger, right? When you're going, yeah, but the without bounds though. That's what I'm saying. Alrighty, now I think this is all for the 6.1. So, yeah, thank you for listening.